Let's now take the definite integral from 2 to 4 of 6 plus x squared over x to the third power dx. And at first this might seem pretty daunting. I have this rational expression, but if we just rewrite this, it might jump out at you how this could be a little bit simpler. So this is equal to the integral from 2 to 4 of 6 over x to the third power plus x squared over x to the third power dx. I just separated this numerator out. I just divided each of those terms by x to the third power. And this I could rewrite. This is equal to the integral from 2 to 4 of 6x to the negative 3 power. That's that first term there. And x squared divided by x to the third, well, that is going to be 1 over x. So plus 1 over x dx. Now, this is going to be equal to, let's take the antiderivative of the different parts, and we're going to evaluate that at 4, and we're going to evaluate that at 2. And we're going to find the difference between this expression, the antiderivative evaluated at 4 and at 2. Now, what is the antiderivative of 6x to the negative 3? Well, here, once again, we could use this as a power rule for taking the antiderivative, or it's the reverse of the derivative power rule. We know that if we're taking the integral of x to the n dx, the antiderivative of that is going to be x to the n plus 1 over n plus 1. And if we were just taking an indefinite integral, there would be some plus c. The reason why we don't put the plus c's here is when you evaluated both bounds of integration, the c would cancel out regardless of what it is. So we don't really think about the c much when we're taking definite integrals. But let's apply that to 6x to the negative third power. So it's going to be, we're going to take x to the negative 3 plus 1, so it's x to the negative 2. And so we're going to divide by negative 2 as well. And of course, we had that 6 out front from the get-go. So that's the antiderivative of 6x to the negative 3 power. And what's the antiderivative of 1 over x? You might be tempted to use this same idea right over here. You might be tempted to say, all right, well, the antiderivative of x to the negative 1, which is the same thing as 1 over x, would be equal to x to the negative 1 plus 1 over negative 1 plus 1. But what is negative 1 plus 1? It is 0. So this doesn't fit this property right over here. But lucky for us, there is another property. And we went the other way when we were first taking derivatives of natural log functions. The antiderivative of 1 over x, or x to the negative 1, is equal to, sometimes you'll see it written as natural log of x plus c. And sometimes, and I actually prefer this one because you could actually evaluate it for negative values, is to say the absolute value, the natural log of the absolute value of x. And this is useful because this is defined for negative values, not just positive values. The natural log of x is only defined for positive values of x. But when you take the absolute value, now it could be negative or positive values of x. And it works. The derivative of this is indeed 1 over x. Now, it's not so relevant here because our bounds of integration are both positive. But if both of our bounds of integration were negative, you could still do this by just reminding yourself that this is the natural log of absolute value of x. So this, we could say, is plus the natural log of the absolute value of x. It's not a bad habit to do it, and if everything's positive, well, the absolute value of x is equal to x. And so what is this going to be equal to? This is equal to, let's evaluate everything at 4. And actually, before I even evaluate at 4, what's 6 divided by negative 2? That's negative 3. So if we evaluate it at 4, it's going to be negative 3 over 4 squared. 4 to the negative 2 is 1 over 4 squared. And then plus the natural log of the, we could say the absolute value of 4, but the absolute value of 4 is just 4. So the natural log of 4. And from that, we're going to subtract everything evaluated at 2. So let's do that. So if we evaluate it at 2, it's going to be negative 3 over 2 squared. So 2 to the negative 2 is 1 over 2 squared plus the natural log of the absolute value of positive 2 is, once again, is just 2. And so what does this give us? So let's try to simplify it a little bit. So this is negative 3/16. Let me do that same color. So this is going to be equal to negative 3, sorry, not negative 3/16. It's got to be very careful. Oh, sorry. Yes. Sorry. Yeah, it is negative 3/16. For some reason, my brain started thinking 4 to the third power. Negative 3/16 plus natural log of 4. And then this right over here is negative 3/4. Negative 3/4. Do that same color. This right over here is negative 3/4. But you have this negative sign out front that we're going to have to distribute. So the negative of negative 3/4 is plus 3/4. Plus 3/4. And then we're going to subtract, remember we're distributing this negative sign, the natural log of 2. And what is this equal to? All right, so this is going to be equal to, and I'm now going to switch to a neutral color. So let's add these two terms that don't involve the natural log. And let's see, if we have a common number, 3 over 4 is the same thing. That is the same thing as we multiply the numerator and denominator by 4. That is 12 over 16. And so you have negative 3/16 plus 12/16 will give you 9/16. 9/16. And then we're going to have the ones that do involve the natural log. Natural log of 4 minus the natural log of 2. So we could write this plus the natural log of 4 minus the natural log of 2. And you might remember from your logarithm properties that this over here, this is the same thing as the natural log of 4 divided by 2. This comes straight out of your logarithm properties. And so this is going to be the natural log of 2. Natural log of 2. So we deserve a little bit of a drum roll now. This is all going to be equal to, the natural log, 9 over 16 plus the natural log of 2. Plus the natural log of 2. And we are done.